Are we settled down? Okay, welcome back. So now we have Mr. Anshuman Nigam from Samsung R&D Institute. At Samsung, he is a principal architect associated with Samsung R&D Institute India, leading beyond 5G research activities and also responsible for part of 5G network development. Product of IIT Kanpur. At Samsung, I think you, Anshuman, you've spent more than 15 years.
Yeah.
Yes.
18 years.
And he has been working on research, development, and standardization for 5G, LTE, WiMAX technologies. He has also served as a delegate from Samsung to 3GPP, RAN 2, and WiMAX 2.0 standards group. Very good. So are you going to talk about that?
I'll talk about 3GPP,
Okay.
The activities going on in 3GPP.
All right. So welcome, Anshuman.
Yeah.
All yours.
Thank you very much. Yeah. So good afternoon, everyone. So I'll try to make the talk short for your interest. In my talk, I would try to cover what is happening in 5G currently. Where are the products of 5G? What are the types of products of 5G which are happening? Then I will try to cover what will happen in 3GPP 5G phase 2, which will be the next set of things. And then a little bit about beyond 5G, that what are the major technologies which we think are important for beyond 5G. So in the previous talks, we had very interesting talks from Satish and Dr. Debrati. So Dr. Debrati's talk was very much into millimeter wave, that what are the challenges in millimeter wave and how we want to overcome those challenges. This is the fundamental technology here. Satish's talk was more from the point where how the products are being deployed and what are the missing links between them. Definitely, as we see, we have the academic research, then we have the industry research, then we have the pre-standards. These three are a little bit tied together. Then there is standards, the development, and the product team. These three are a little bit tied together to each other. When we conceptualize about an idea or a technology, even let's say millimeter wave, we start from the academia, and by the time it reaches the product, the vision which was seen here, the final version is a little smaller than that because of many things, because of many constraints, practical constraints. But that's the nature of this research, and that this will happen even in future technologies. So my talk will just focus on the part of pre-standards and the industry research activities. So let's first see 5G. It's a reality now. I mean, 2 years back when we were having such workshops about 5G, then it was like what will happen, what will come. But now it is a reality. You see, before we go into the actual deployments of 5G, let's just do a recap of what are the main elements of 5G. So main elements of 5G, if you start from coverage capacity everywhere, why in the first place we need 5G? And back in 2011-12, when we were forming the vision document for ITU, that we are trying to draft the requirements for 5G. So requirements which could not be met by 4G. For those requirements, we conceived a vision about 5G. So one of the things that was, when we started, we wanted to visualize very immersive AR, VR applications like holographic calls, which again may not be a reality very soon. So the point I'm trying to say is that we visualize things, but the first products when they roll out, they are not in comparison to the first visualization that we have done. That's the nature of how things proceed. So holographic calls, let's put it for a little bit for beyond 5G or beyond that. So coverage capacity everywhere, low latency, ultra reliability for various types of use cases, more battery life, unified spectrum, scalable from the perspective of the core and the software perspective. It should be scalable and easily deployable. There has to be service continuity and smooth interconnectivity across the radio technologies. So these are all the principles based on which 5G was designed. We see from the standards timeline perspective, as you may know that release 15, which is the first release of 5G, that was completed in June 2018. And then one more version in the end of June. The next release of 5G is called release 16. So it will contain more technologies which will add to the bare bone 5G. Release 15, you can assume it is like a bare bone 5G. This release will be out in the December of this year. Some of the work, I'll talk about some of the important work items here, and some of them may get extended. Now, when you see this above timeline, you see that there are some of the operators who are already planning for 5G, already deployed 5G. So that's the reality that is happening. In fact, even we didn't thought that in 2019 so much deployment of 5G will be actually done. I have a couple of slides later about it. When we started 5G, there were various possibilities. Can we go for a greenfield deployment of 5G, or it has to be a gradual step-by-step deployment? So because LTE is also widely deployed, we can't do away with LTE. Obviously, a lot of money has been put in there. And also because 5G, first version of 5G, which was thought about millimeter waves. So there were chances that how well it will work, we don't know in real field. So 4G acts as a base controller for 5G. So 4G provides a base connectivity, and whenever there is huge data rate required, 5G can be switched on for that. So that is called the non-standalone deployment, where 5G doesn't work on its own, it works with the help of 4G. So this is the first path. We go to first non-standalone. We set up the system, we experiment, we see in real field the working of 5G, then we gradually go and cover the entire geographical space with 5G, where 5G can work on its own. So that's called the 5G standalone, 5G non-standalone type of migration. What actually 5G gives us, right? So obviously there, in the morning talk we had, the different view from the operator that even massive MIMO, which is supposed to give a linear increase, it is just giving 1.2x. But those are the practical challenges that we have to overcome. But in the first place, when we designed 5G, why we designed 5G, with what technologies we designed 5G, so what it was expected to give. It is expected to give a peak throughput of 20 times. And how do we achieve those 20 times? Primarily by the large bandwidth. So these are the actual enablers for this, the key enablers for this, the wide bandwidth. Then there was a thought on to increase the spectral efficiency. Even though we are operating close to theoretical limits, but there's a lot of overhead built into the system. Can we do away with that overhead? Can we minimize that overhead? That is the concept of the lean system design. For example, in LTE system or any 3G, 4G, 2G system, there's some system information which is the essential information that is broadcasted by every cell. That is a periodic broadcast. Now here, we try to reduce that to bare minimum and make it say that this broadcast will happen only when needed. So this very essential default broadcast of the system information. Remaining all the information will be broadcasted or transmitted by the base station when it is really needed. Similarly, there are MIMO enhancements which contribute to this spectral efficiency, especially the feedback, because MIMO, as you know, is purely dependent how well MIMO you do. It depends on how well channel state information you have at the base station. Then there is the ultra low latency, because we wanted to bring the latencies down from tens of milliseconds to ones of milliseconds. And why we want to do that? Because there are services which require it. For example, robotic healthcare. So there are services which require it. So because of that, we want to do 1/10 of the latencies as compared to 4G. How do we achieve it? We achieve it with the concept of multiple numerologies. So the time slot has been made shorter in 5G. So in 5G, the time slots can be of varying lengths. There are many different possibilities of time slots. So the lower versions of them are designed for low latency. And a beautiful thing about 5G is the multiple numerology concept, where your OFDM grid, you can divide. The part of the grid, you can have a shorter time slot. Part of the grid, you can have a wider time slot to cater to different service types. So that is the one thing which actually leads to the low latency. The UE energy consumption, so in terms of we want to make it practically half, though if you ask me today, if you see the 5G phones, they heat up in few minutes. So there's a long way to go there. But from the standards perspective, at least, there are things which are done to reduce the energy, especially from the related to the DRX and DTX kind of operations. So we transmit when required, we try to receive only when needed. We try to optimize on that. So this is the key summary of the expected performance enhancements of 5G over 4G. Now coming to some things which are happening now. If you see, there are 26 commercial solutions which are already there, 5G launches. 26, which is a big number actually, and expected to have 55 launches this year. We didn't expect it that much, to be honest, especially the US operators, the Korean operators, and also now European operators are coming into picture, if you see. Here, I'm not sure if this is visible, but the projection by GSMA is that by 2025, 15% of the mobiles will be 5G. So that's from a recent GSMA thing. So we are expected to have 55 commercial 5G networks by the end of this year. So this year was supposed to be an initial development year for 5G, but it turns out that operators are willing to put in money for the actual deployments. Korea was the first country to launch the commercial 5G service, and now they have 2.5 million users. And when I was talking to my Korean colleagues and friends, the key service there right now are two. One is the AR, streaming AR service. So streaming AR VR service and the cloud gaming service. These two services are given by the operators, and which are becoming very popular. People are buying headsets, 5G handsets just for this purpose. Samsung is one of the largest suppliers for 5G base stations. If you see, there are 86,000 base stations already deployed in Korea, 5G base stations. In the US, it is the things were started by Verizon, and Samsung was part of the first development of 5G task force by Verizon, which was an internal standard of Verizon to develop something on the millimeter wave, primarily because they had the millimeter wave spectrum. So today, if you see in AT&T, Verizon, Sprint, T-Mobile, there are a lot of trials and initial deployments which are happening. Samsung, Ericsson, Nokia are the key vendors from the network side. From the handset side, it is Samsung, and then there is Qualcomm-based modem solutions in with various vendors. In fact, third-party speed test done by TechRadar guys in Chicago, it was observed consistent 1.4 Gbps average speeds, which is a big thing as compared to LTE. You know, for example, for you guys, like you can download Stranger Things in 40 seconds as compared to 1 hour plus in 4G. So that's a big thing. From your perspective, that's the thing that you need, right? Latencies are down to from 30 milliseconds to 17 milliseconds. There's more scope here, as I said. 5G has multiple time slots. In the current deployment, the shortest time slot is not yet deployed. So the services are now present in various cities, around 20 such cities here. In Verizon, also in 9 cities is present. And a lot of portion will be covered by, US will be covered by this year. In fact, Samsung Galaxy S10 is also available with 5G version. Samsung Galaxy Note 10 in Korea is available with 5G only. There is no 4G there. It's 5G only, I had. This is the 5G Europe. So Europe was a little delayed as compared to US and Korea this time. And in Europe, the bands of operation primarily are sub-6 gigahertz band. And obviously, the bands of operation depends which bands are available with the country. In Europe, as a geography, 3.4 to 3.8 gigahertz spectrum is more widely available. So countries are going ahead with that deployment. In India, things may happen next year, maybe. So we at Samsung have a host of products, right from the access unit, the baseband unit, the access unit, the radio units, and the core network. And we are into both the mobile side and the network side. So we have an entire set of products for both the 5G network and the 5G mobile. And this is what we are deploying in the actual Verizon and other operators and in Korean operators. So this was the current snapshot of what is happening in 5G. So it's going to reality at a faster pace than we accept it. Then I'll quickly touch upon few basic attributes of 5G from the standards perspective. So when the design of 5G standards was started, there were 3 key attributes which formed the base. One was to make it flexible. 4G was designed for a specific purpose, but 5G has to cater to broadband type of service, ultra low latency, or massive machine type communications. So the requirements are very varying. So the 5G standard was designed with more flexibility in mind. When we say more flexibility, what does it mean? It means that giving you an option to do things when they are needed, so on-demand reference signal, on-demand system information. Flexibility in various ways, in time, in organization of the frame structure. This flexible so that it can adapt to various types of higher requirements. Diversity. So from the core network perspective, we are designing the entire network as kind of a network slices. So when we have network slices, each slice can be used for a specific purpose. Each slice may have different requirements. For example, a slice of hospital purpose may have a different requirement in terms of latency versus a slice of AR/VR. So operators can tune their network. They can partition their network efficiently by using this network slicing concept, which is recently introduced in 5G. Third thing is from the deployment perspective, the scalability. So as we were discussing in the first talk, things are moving towards pure software. So traditionally, if you have a look at 3G or 4G network, the vendors like Samsung, Ericsson, Huawei will be giving to the operators of fixed boxes, which will be customized equipments on which the customized software runs. But here the trend in 5G is to move towards pure software kind of deployment, where those software should be able to run on general purpose, for example, Intel Xeon machine servers. Why that is required? It's from the operator's perspective. They will have more control on what to buy from here, what to buy from there. They will not be tied up with the physical hardware which is available. So this is another major change which is happening. For that, the core, 5G core was redesigned as compared to 4G core. Even though the functional elements may look similar, sound similar, remain similar, but the way in which it will be implemented will be different. So the entire thing, in fact, Professor Devrati was talking about Cloud RAN kind of stuff. So we are actually implementing those Cloud RAN, where the radio remote heads will be out. The base stations will be only antennas connected via optical links, EC-PRI links to the Cloud RAN. All the processing happens at the Cloud RAN. So what does it imply? It implies that software is going to play a very major role at the Cloud RAN. You have to write the algorithms, especially the physical layer algorithms, such that, for example, channel estimation, it completes in the given time. Now your time is further shortened because you'll have to account for the delay coming from radio remote head and going back. So your time is further shortened, but advantage that you have more data of various base stations together. So you can do joint optimizations. You can come up with joint schemes. So that's the, So that's the key philosophy of the 5G standards. It's based on these principles. A very short comparison between NR and 5G. I think you all are aware about this, but so in the interest of time, I will skip few things. So the time slots are shorter. The carrier bandwidth is bigger as compared to 4G, and the beamforming and hybrid beamforming and MIMO is the main technology which is used. Carrier frequency is also different. We are going to millimeter waves and higher sub-6 gigahertz bands for 5G. Second difference is between the core of 5G versus the core of 4G. So the core of 4G, as I mentioned, is more of a fixed entity. For example, today in 4G core, if you are adding, let's say, a lot of users, the control portion of the user, the resources that you give, the software resources that you give for the control portion of the user and the data portion of the user, they will scale because you're just adding by numbers. But in 5G, I can scale the control in a smaller way and data in a bigger way, because that's what ultimately is required. You want to allocate more memory for data, not for control. So that kind of flexibility is given. Things are moving towards more software, pure software domain. Just let me know how much time I have. Yeah. So from the 5G RAN perspective, some of the key things which we should be aware of as technical guys, we should be aware of how this data processing is happening. When we are going from 150 Mbps to 100 Mbps to 2 Gbps, 3 Gbps, one thing is that on the physical layer, your physical layer should provide that. So that's why we have a wider bandwidth to do that. The second question will come is on the implementation part. How do you process that? Is the standard tuned for that? So that's the point here, the data processing, the GBPS requirements of data processing. So we have a simplified layer 2. The data processing layer, they are simplified in a way such that it can enable faster processing. So for example, there are 100 packets coming, and you have the headers of each packet separate. They are not linked to each other. So you can now process those separate headers in parallel in hardware. You can design your ASIC for that. Then you have higher reliability. There is packet duplication for signaling and some of the data. You have, from the power saving aspect, you have on-demand system information, you have bandwidth part. For example, when I said the bandwidth will be 400 megahertz in 28 gigahertz frequency range. Now, if you always have to open that 400 megahertz, there will be huge amount of power consumed at the RF level. So you don't want to do it. You want to use 400 megahertz when you have, let's say, 3 Gbps, 4 Gbps data requirement. But if your data requirement is, let's say, 1 Gbps, then you don't need whole, you can cut it to 100 or 150. So that is called the bandwidth part, where is the dynamic configuration of the bandwidth for the UE as needed. In LTE, it is not like that. LTE UE typically will be 20 megahertz UE. It will always open the 20 megahertz. And the max power consumption happens is in the RF portion. Okay. Then, from the core side, as I have earlier mentioned, it is primarily for virtualized deployment. That is the main thing, and giving you control at a finer level. So for example, finer control of QoS and virtualized deployment. That's the main factors for change in the core of 5G. So this was the basic key things about 5G phase 1, as we call it. 5G phase 1 release 15. That's the bare metal 5G, you can call it in one way. That provides you with the very essential things, but not all aspects of 5G as we visualize at the start. So to cover the remaining aspects of 5G, they are called as 5G phase 2 or referred to as release 16 in 3GPP terminology. I am going to list few of the key tech items which are currently are in the standards phase, where people are working on it to create it. I'll explain a little bit about each of them, each of these items. Yeah. So in 3GPP or in general, you divide the things into radio side and core side. So when I say RAN, that is the radio side. When I say SA, that is typically towards the core side. So from the radio perspective, the key things which are going on, and these are the things which are of interest as a student community, as a research community, these are the things which are going on. These are not complete, which means there are chances to contribute to it, to identify new problems within these, file patents, and contribute to it. So the unlicensed technology. So typically cellular systems work in the license range. But even in LTE, we introduced unlicensed, LTE unlicensed. So LTE can work in unlicensed frequencies range, similar to Wi-Fi. So this is, you can say, as a competition to Wi-Fi. So similar thing is carried forward here in 5G, where NR in sub 6 gigahertz operates in the unlicensed mode. So it's still under the standards process. When you say it will be unlicensed, there will be a lot of changes to the current licensed spec of LTE or 5G. For example, right now we define that the 5G base station will be in control. I am transmitting to the UE here. I expect a feedback here. All these are fixed. But when you go to the unlicensed one, your neighboring entity or neighboring node of Wi-Fi can grab the channel. You cannot be sure in time. Because of this lack of surety in time, many procedures will be impacted. So that's the main thing there in unlicensed. Second thing, you have to coexist there with the Wi-Fi technology. You cannot harm the Wi-Fi technology, so you have to have a fair share of the channel usage. So there are certain requirements defined for that. We need to define the technology to be compatible with that. Second thing which is there is called industrial IoT. So that is more related to that in a factory, you can put up a 5G network. Now all the robots and the factory machines can communicate, IoT the systems can communicate to each other. So the main thing there is the redundant links to ensure the reliability, optimize redundant paths to ensure the reliability. Third thing is the RAN data collection. That is coming from the AI. So in 5G, 3GPP is enabling that system can make more use of AI. Now to make more use of AI, the first thing required is data. Now if 3GPP doesn't define that this UE can send this data to the network, then UE will not send the data, the network will not have the data, and if network doesn't have the data, it will not be able to apply those AI algorithms. So this is a work item in which we identify what are the information of interest and send it back to the network. Then is the relays. Because going with the 5G network, relay was a topic in 4G as well, but didn't pick up because it was not required, that much required. But in a 5G network, when we have cells of the size of 150, 200, 250 meters, it is very and given the millimeter wave channel propagation characteristics, it is very likely that just one shot hop may not be enough to reach the final network. So relays will be needed. So relays will be an essential part of 5G if you want to have a large scale, dense 5G deployment. So this is a topic which is coming back. It was originally in academia for quite a few decades. So this is a very hot topic right now. Then is the EV2X, which is to enable vehicle-to-vehicle communication. The changes required in the standards to enable vehicle-to-vehicle communication. Then this is the ultra-low reliability part. So in the current first release of 5G, primarily the data rate was addressed. The reliability portion was not addressed much. So here things are being added to enhance the reliability. Okay. Similarly, from the core side, there are few of the work items which are, some things are common, like V2X is common industrial, because you have to do something on the radio side, you have to do some part on the core side. V2X, industrial IoT, network automation, which is the collection of data, which Satish also mentioned in his first talk. So in this, the key thing is that 3GPP will only enable the sharing of data across the various nodes. What you do with data is up to the vendor. It is a vendor differentiation. If Samsung can have a better algorithm than Huawei, then it will have advantage, for example. So this is the network automation. The 5G LAN, which you see, is kind of a private deployment of 5G, which may be possible now. For example, in IIIT here, if you want to have a private network of 5G, like you have a private LAN, it can be done with this. And this is another important topic, which is called mobile edge computing. So today, the maximum that we do is we send the information or the processing, we offload it to the cloud. The moment when we say to the cloud may be anywhere. Actually, the processing may happen anywhere. And if, let's say, the processing is happening in New York, the time it takes to travel to New York for this information and coming back cannot be avoided. But that will impact the latency, because this timing is of the order of more than 50 milliseconds. But for various AR, VR use cases, considering the human perception limits, the order of latency is required of within 10 milliseconds. To enable that within 10, 15 millisecond range, you need to offload the processing to a neighborhood node, a nearby node, not to any generic cloud server. So here the concept of MEC comes in, where MEC means effectively that you have a computing node at the base station. So you offload the computation to the base station. Now where this is used, for example, in AR, VR streaming. Not everything is possible to do on phone, because phones like Galaxy S10 and Note 10 are highly capable, but let's say some other devices are not capable. So it depends how much GPU you have in the phone. It may not be possible to do all the processing. If you have to do, let's say, 4K processing, you can do it at the base station in the MEC environment, and the rendered final stream can be sent to the users. That is what the service I was talking about in Korea, the AR, VR streaming service. So this is another big thing which is happening. Now, just moving on to very few two topics beyond 5G, which are beyond this. So from an academic research community perspective, I personally feel these are the two topics which are of very great interest. First one is the aerial communication. So aerial communication involves any entity of the network. For example, UE, not only UE, base station, both can be flying. Both can be anywhere, can be in drones, can be in satellites, can be in high altitude platform systems. So this is what it represents. This is also called in 3GPP terminology as non-terrestrial network, NTN. So what are the benefits of it? It always.
Can you also say what are the challenges?
Yeah, I will point to it. So this benefit it will give you is very large coverage. So from Indian perspective, the rural connectivity can be there. Connectivity basically can be guaranteed. Another interesting thing is there is the on-demand coverage and capacity injection. For example, if you have higher demand today here in IEEE, then few drones can come as base station and enhance the capacity. The drones at the backhaul may be connected via some other wireless link. This is the main thing actually for this. So there are various versions of it. You call it drones, you call it HAPS, and then you call it satellite. Satellite has LEO, MEO, GEO levels.
So,
yeah.
I wanted to ask you.
Yeah.
When you have flying facility for connecting, does the spec cause any limitation on the speed or the?
Right now the specs are not there for this. This is a release 17 item.
Okay.
So specs will come into picture, primarily because the satellite industry has also entered 3GPP, so they are driving this. So the specs are not there right now.
Okay.
If you see if you go and search for NTN 3GPP, you will find a current technical report of it. So the speeds are being targeted, high speeds are targeted. There are various obvious challenges which needs to be overcome. Quite a few of them are non-obvious. I can't just use the current standard of 5G without changing this frame structure. Can I do it? No, it won't be possible.
And Doppler also will come.
Doppler, I have listed that. So these are the use cases, and coming to the constraints and key issues, right? So there will be high path loss, you can't avoid it. There will be high transmit power requirement on the UE side, on the node handled side, unless you come up with a hybrid scheme where the downlink is from the satellite or these drone systems, and the uplink you send it to the regular network from the perspective of power, because your handheld device will not have enough power to send the transmission to satellite, right? So those thoughts are there, nothing is freezed yet. Then base station mobility will lead to large Doppler shift. If the satellite is moving, it will lead to large Doppler shift. We need to overcome it. The feedback mechanism, the TDD, when you send a packet, the acknowledgement of it, huge time is required. So how do we design the frame structure for that, right? In fact, the channel modeling itself is not there, right? Because from satellite to a higher altitude, let's say airplanes, it is simple. But the moment it comes here, it scatters here. That channel model is not there. You will uplink power consumption anyways is required. The HARQ procedure, because of the delay, is required. Large propagation delay. So large propagation delay and high speed of the base station leading to high Doppler. These are the two main things: Doppler and delay. Yeah. Yeah. Yes. I think it's hundreds of kilometers, maybe 200 to 300, something. Yeah. Yeah. Channel model, I personally feel from geo to LEO it will be less affected, but the moment you consider the ground here and the the various buildings and reflections and scattering here, that is what impacts the channel model more. For the LEO case, for the geo case is still easy because the base station will remain fixed kind of thing, but for LEO the base station will change. So it will be, the mobile is here, but the base station is changing. So it's kind of a reverse handover that has to be designed. Right now, UE moves, mobile moves, and it changes the base station, switches the base station. But here, mobile is static, but the base station is changing. Low, yeah, you can say that, the low orbit satellites. Yeah. So these are all the issues which are listed here. There are a lot of things that needs to be done. Many of it is not done. So this is a very interesting topic for academic research. Yeah.
There was a initiative called mobile satellite channel modeling.
It may be along that lines.
So mobile satellite channel modeling. Basically, it was targeting this type of application.
Quite possible.
If you remember, where actually all these disasters were happening,
Yes.
so that time people came up with a solution that let us have a disaster report based on the
Yes.
satellite. And that should be the LEO satellites. And then whether we can go ahead with the under the framework of the 4G to some extent, second 4G also. But there we got stuck because of this channel models.
Maybe things would have progressed here, but at least not in 3GPP. But the ones that you are saying, those might be the input to 3GPP in later years. In fact, SpaceX is doing the same thing. They are taking the LTE and they are changing it to adapt to this kind of scenario in their own way, not in a standards way. They're proprietary standards. So, yeah. If you see this short industry landscape, so SpaceX is leading it thing. And there are, even Facebook had that, Google had that Project Loon. And there are various other industry players, primarily in Marsat, Viasat, Hughes, OneWeb. They are entering into 3GPP and trying to dominate this type of work item. So I have listed the TR numbers if you are interested. If you just search on Google for this, you will get it. It's a good technical report actually. Some more industry traction is also happening here, IEEE, ICC, and other conferences, CCNC. It's a call for papers for that. So this was one topic in short, and the last topic is AI. So yes, you can do many things on AI without actually standards, but as I said, what will a standard enable? Standard will enable the sharing of the base information based on which you will actually come up with the AI schemes. If you see, just with a very, very open perspective, what things can be done in AI. So on the handset side, we typically notice we are going and, sometimes the call fails. They are called drops. It may not happen always, but maybe you would experience that 5% of the time. 5% is a lot of time if the call is dropping. So can we predict that the call is going to drop? If we can predict, then we can take some corrective action. Similarly, from the beam perspective, when you are holding the phone like this, your best beam pairs are something. When you change the orientation or you move, it changes. If you have to do the beam search again, it is very costly in terms of power. So can I predict, okay, possibly these three only. Let's first try among these three. So that's the thing, that is another thing which is important. Similarly, there are many things actually. From the traffic estimation and scheduling perspective, for example, we had a discussion on a scheduler in the morning, right? So scheduler is a very complex and proprietary thing. But schedulers, how are they designed? They are designed in a way that you come up with the certain heuristics and closed form mathematical solutions for specific scenarios. They will work the best in that scenario, but that scenario will always not remain. The scenarios will keep on changing. So it's a suboptimal solution in practice if you see. So can we use AI to actually remove that fixed form equation, and it can decide the best thing at that time in the with the given constraints. So that's something that you can do. There are a lot of in physical layer autoencoders, for sure. I maybe not in the beyond 5G era, but definitely in the 6G era, the wireless protocols, the way it looks, it will not be the same. It will be largely AI based, and similarly on the core you have huge amount of data, which means that you have huge opportunity to apply AI in various forms. And that is the first place where actually business products will come out here. For example, fault prediction and self-healing. That will be the things that will come out here. This is still in academic research level. A lot of things need to be shaped up here to go to the industry research. This is a more detailed summary of what is happening in 3GPP about it. Just to say that there's a fair amount of work which has started on it. Sorry. And this is the last slide. What is happening in IEEE and in industry overall? So IEEE dedicated journals have started for AI in wireless. It's a big topic covering from physical layer till higher layers. Physical layer especially has a more dedicated journal here. And the primary things which are of interest, I have listed all of them in the first slide. Primarily it is autoencoders, which do the modulation and coding on their own. They decide on their own. People are trying to attack every aspect of cellular communication and trying to do away with the mathematical aspects as much as possible. Let the system learn on its own. So these are the two main things where I think academia can focus on. And there are various summits which are happening. Those are separate things from the industry perspective. But these two, aerial communication and AI in wireless, are the two big topics where I personally believe that as an academia we should put some dedicated focus. A lot of it needs to be done here. Thank you.
Thank you, Anshuman. So that's the beauty, academic. When you attend an academic lecture, you understand the concepts in deep, and when you get industry veterans, they tell you how to get them onto system to work.